Alright folks, we're back with another episode. Today we're going to do extreme values of a function. Of course, by a function here we mean a multivariable function of at least two variables. Now I'm going to assume throughout the class we're doing this with a function of two variables. You can extend this very easily, everything we do very easily, to a function of more variables, 3 variables, 4 variables, you name it. You just have to look at more partials. I'm going to talk about it in a second. So let's let f of xy be defined on some domain on D, some domain D, okay? And let AB, the point AB, let's let the point AB be an element, be an interior point. Let be an interior point of D. Okay, so first of all we need to define what it means for a function to be a local minima, and then what it means for a function of local maxima. I guess we'll do the max first. They're just opposites of each other. So when do we have a function of the local maxima? We're going to have if f of AB is greater or equal to f of xy for all xy in some open disk containing AB, then AB is a local min. Local max. Sorry, we're doing the max first. Local max. Okay, local max. Now, if you do the other way around, if on the other hand, let me push this up. We have the other way around. F of AB is less than or equal to f of xy. Let me use this simple. Remember, this means for all xy in some open disk again. Open disk containing AB, then AB is a local min. Okay. Well, it's not AB that's the local min. It's actually f of AB is the local max and local min. So we're talking about the maximum value and the minimum value, okay? So the point, actually, the way to write this is the point, we're talking about the point A, B, and the z coordinate is f of AB. Okay, so that's where that point is the local max. Okay, similarly, AB, f of AB would be the local min here. Okay, let's talk about, so again, this is all mumbo jumbo. It's a lot of writing. Nobody likes looking at this stuff. So what is it going to be when we're talking about three-dimensional picture? Let's take a paraboloid like this. Okay, we have a paraboloid like this. So this would be the local maximum. Okay, local maximum, kind of thing we're used to from Calc 1. And if you do it the other way around, something like this, okay, it's going down, something, it's open down, it's like this, okay, or it's like this. This is maximum, this is going to be a minimum. This point here would be a local min, and this would be local max. Okay, so if we look at our old trusty lemon here, okay, so the top would be the max, this point would be the max, the bottom point would be the min. Basically, that's what it would be. Okay, so now we do have tools to determine where these points are. Again, if we think about our good old Calc 2 days, if this wasn't like this, if it was just a function like this, the two variable, what were we looking at? We were looking at points where the tangent was flat, it had zero slope, so where the derivative was zero. Now here what we're going to note is one derivative is not enough. I'll show you an example why one derivative is not enough. Here, you need at least two derivatives, okay? So you have this derivative, say in the x direction, sorry, the x direction is like this, the x direction and the y direction, okay? Those two derivatives are both zero, right? Any derivative here is just zero, okay? They're all flat. And similarly for the bottom. Here, they're not flat, right? Many of the derivatives they're just not flat. They have the slopes have some value, okay? So this carries over. We can write down the first derivative test. We need to have the derivatives to be zero. First derivative test. So this is exactly the same from single variable calculus, but we're going to look at two variables now. If f of xy has AB as a local maximum, local max or min, okay. Here, of course, remember AB, we're talking about when it's local, it's got to be an interior point of the domain. Okay, so that's very important. You can't do these on the boundary. On the boundary, you have to do something else. We'll talk about it later on. If we have f of xy AB has a local maximum and minimum, and the first partials exist, and if x and fy exist, okay, if they exist, then what needs to happen is they need to be both zero. If x equals f sub x equals f sub y equals 0. Okay, they just both gotta be 0. Yeah, so let's think about this a little bit, and maybe do a very simple example. Let's do a very simple example. Let's say I have z is equal to x squared plus y squared, right? Okay, so I look at z sub x. This is differentiable everywhere, so you could just get 2x. And z sub y, the y derivative, you get 2y. Okay, so this equals 0. Z sub x equals 0 implies immediately that x equals 0, and z sub y equals 0 implies, of course, y is equal to 0. Okay, so we have this point x, this point 0, 0. Okay, 0, 0 is a candidate, right? Is a candidate local extrema. I don't know which one it is right now. We have to develop a way to do it. Local extrema. Okay, we have to develop a way to tell whether it's local minimum or it's local maximum. It could be neither also. So in this case, we're lucky enough that we know how to draw this, right? So this is going to look like this. So at the bottom here, at 0, 0, right? This is going to be, we know that it's a local minimum. The question is, okay, so it's the good old game of taking the derivatives and setting them equal to 0, but we have the same problem we had in single variable calculus, and the problem here is when the derivatives are 0, you might have many things going on. You might have a local maximum, you might have a local minimum, or it might be neither of those. So we need a way to tell the difference. Now, when we were doing Calc 1, the most surefire way, the surest way of doing it was making a derivative table for the values. If you go review your Calc 1 material, right, single variable calculus material, you'll see how to make those derivative tables. Now, we're talking about two-dimensional. The domain is two-dimensional here, so doing tables is, yeah, it's going to be a little harder. We're not going to do tables. Instead, we want to find a way to tell them using the second derivative test. Remember, we had the second derivative test for single variables. We're going to develop a second derivative test for more than one variable. Okay, at least two variables, functions of two variables. Now, so our issue is okay. So we know points where both f(x) equals fy, they're both 0 at the same time, they both gotta be 0 at the same time, are candidates for local extrema. Okay, but the question is, how do we tell when we have a max, or a min, or neither? Okay, making tables is just, it's a no-go. It's going to be too complicated. All right, so let's talk about our candidate points. Where could be the points where you have a local maximum? Well, the theorem we just said now is not an if and only if. It said if the derivatives, let me just put it back again. If the first derivatives exist, okay, at the local maximum or minimum, at the local extrema, they gotta be 0, okay? So it's, if they don't exist, of course, they don't have to be 0. Can you have a local maxima and minima where you don't have the derivatives existing? Sure enough, okay. If you take a cone like this, like think about an ice cream cone upside down or just normal, here the derivatives won't exist, right? Because it's a corner. Okay, so to find extrema, I have to look actually at two kinds of points. Points where both the partial derivatives are 0 and they don't exist. Okay, those we're gonna call them to be the critical points of f. So interior points of the domain. So this is going to be another definition. Interior points of the domain of f of xy. Let's do two variables, f of xy, where f of x, fy are both 0 or don't exist, are critical points. Okay, so what is a critical point? These are candidates for extrema points. Now, a critical point, finding the critical points is not enough. A critical point might be a maximum. It could be a minimum, or it could be neither. Okay, it is possible that you have it being neither. Okay, so you could have three types of critical points. Now this is what we're going to usually talk about. This is a saddle point usually. So let's define that. How do we have a saddle point? It's interesting. You could have let's talk about the saddle point. So the name kind of says it all. I'm gonna try to draw this actually. Hold on. Let's see if I can do it. So it looks like a saddle basically. Okay, it looks like a saddle like this. Okay, or a horse saddle. So if you look at this point here, right? Now, because it's a saddle, it's the lowest point of the saddle, but it's kind of the highest point on this, okay? Because this is a surface, right? This is a surface. Let's try to shade it in. Maybe the light is coming on the other side, so this side is dark or something like that. Okay. Now it's higher than all these points here, and it's lower than all these points here. So what classifies as a saddle point is you have this point, and you have an open disk containing this point, and no matter which point, we have this point AB. Okay, this is the guy. And no matter how small an open disk I take, okay, there's always points greater than it, okay, on the ridge of the saddle here, and there's always points lower than it on the sides of the saddle. Okay, that's a saddle point. That's a saddle point. So let f of xy be a differentiable function. And let's say AB is a critical point. AB be a critical point. Okay, so let me push this up. I don't want to go out of bounds. Let's keep the saddle in the picture. If every open disk containing AB contains points xy such that f of xy is less than or equal to f of AB, okay, and also contains points okay, also contains points where contains points, let's give them names again, contains points, let's call them xy again, they're different xy. F of xy is greater than f of such that, let's say such that f of xy is greater or equal to f of AB, then AB is a saddle point. Okay, so this is bad news. Bad news. We're going to handle it very easily later on, but right now it looks like bad news. Let me tell you why it's bad news. Because we got this idea, okay, I'm going to do the x derivative, I'm going to do the y derivative. If they're equal to 0, this is going to be some kind of maximum or minimum in our heads. But here, as you can see, if you do the derivative in the, let's say, x direction, the tangent is going to be here, and that's going to be 0. If you do the derivative in the y direction on top of the saddle, right, it's going to be this way. It's sorry about that. It's going to be this way. Again, the derivative is going to be 0, okay? So you have both the partials 0, but unfortunately, it's neither a maximum nor a minimum. It's a saddle point, okay? So that could happen as well. So now we're going to develop a new way to tell the difference between all these types of critical points, okay? At least when the function is differentiable. When the function is not differentiable, it's kind of hard. It's going to be when it's not differentiable, it's kind of hard. We're going to see examples where it is differentiable, and then move on from there. So the second derivative test. This is analogous to the second derivative test from single variable calculus. So let's move the paper right. So second derivative test. Here we're going to look at the second derivatives of the function, and what we'd like to do is assume let f of xy have continuous first and second derivatives. Of course, I mean, it's kind of, this is not necessary, right? If the second derivative is continuous, the first derivative, if the second derivative exists, the first derivative has to be continuous anyways. So you could take it out and just say, if it has continuous, I just wrote cont for it, continuous second derivatives. On a disk centered at AB, and fx, let's let fx be equal to fy, and let's say they're both of the partials are 0. Okay, then we have 3 cases here, and we're going to talk about these 3 cases. So we have a function that has continuous second derivatives, which immediately implies it has continuous first derivatives, centered around AB, so it's differentiable on some open neighborhood. And then we have a critical point, okay? F sub x and f sub y is both 0. So now we're going to look at the following. If we have this funky term, f sub xx times f sub yy minus f sub xy, the whole thing squared, what's going on, is greater than 0. And if xx is less than 0, then we have a local minimum at AB. Okay, so what's going on here? What's going on here? Okay, we have this funky term. This is called the discriminant, or it's the Haitian. We have this funky term. Okay, I'm going to talk about this funky term in a second. So this is very interesting. We didn't talk about where the first derivative came from. I said it was kind of obvious because remember from the pictures, I mean from the lemon, right? It was just down to partial derivatives. You just looked in the x direction, then it gave you a single variable curve. If you look at the y derivative direction, it gave you a single variable curve. So if it was going to be a maximum or a minimum, then the first derivative test for the single variable calculus, right? The proof of the first derivative test. You might want to go back and review that. Actually, it's a very nice proof. You do two-sided limits there. This has got to be 0. This has got to be 0. It says at a maximum and a minimum. Now we have a problem though, because it says the problem here is our saddle point. Let's go back to the other picture. Here, both of the derivatives were 0 also, but it wasn't a maximum and it wasn't a minimum. So what this term says is that locally everything is heading the same way. Okay, you don't have one direction going up, you don't have another direction going down. Okay, one direction concave up, one direction concave down. You don't have that. If one of them is concave up, everything is concave up. If it's opening up like this, like my hand is opening up like this, everything is opening up. If it's opening down like this, like the lemon, okay, every partial derivative in every direction is opening down. They're all concave down. That's what guarantees, this term guarantees it. I'm going to talk about it in detail in a second. So everything is, what this is, everything is opening up the same way. They're all concave up or concave down. Remember, this was concave up. This was concave down, okay? So here, what do we know from fxx? Well, if the second derivative in the x direction is less than 0, that means in the x direction, the function looks like a curve like this, okay? So it's got to be, since everything was opening up the same direction, they are all pointing down, so this has got to be a local maximum. Oh my goodness, I said local min here. Sorry guys, my bad. Sorry. It is a local maximum, right? Okay, but that's my bad. I'm sorry. Okay, so similarly, again, if everything's opened up the same way, they're all heading the same direction, and you have fxy squared, again, it's greater than 0, and this time, you have the function being concave up. You don't need to look at fxx. You can look at fyy. It doesn't matter which one you look at. You just pick one that you like. And if it's greater than 0, so it's concave up, then AB is a local min. Okay, because it's opening up. So what's happening here in the x direction is we have this. It's going to be a local min. Okay? Now, if, on the other hand, if we have fxx times fyy minus this term fxy squared, I'm going to talk about where that comes from. If this is less than 0, then f has a saddle point. So they're hitting different directions. Saddle point at AB. Okay. And number four, if fxx times fyy minus fxy, the whole thing squared, is equal to 0, the test is inconclusive. You cannot make a conclusion. It could be a local maximum. It could be a local minimum. It could be neither. Okay. So that's the test. You have this term where fxx times fyy. We're always looking at this term. If it's greater than 0 and the derivative locally is concave down, then it's got to be a maximum. If it's greater than 0, that means every derivative is heading in the same direction. And if it's greater than 0, well, guess what? It's concave up, so it's got to be a local minimum. If it's less than 0, that means the derivatives are heading in different directions. You know, they're doing weird stuff. Sorry, not this is heading the same direction. Like they're heading like this. Okay, they are heading different directions. You have kind of like a saddle going on. Okay. So in that case, this is going up, concave up. This is concave down. Then you have a saddle point, and here when it's equal to 0, you're inconclusive. So where does this term come from? Okay. So what is this term fxx times fyy minus fxy squared? Well, why is it called a discriminant? Because it's a discriminant of a matrix. So if you know a little linear algebra, I'm gonna just write down a discriminant for you. Determinant, sorry. I'm gonna write the determinant for you. If you don't, that's fine. Just memorize it. So what this is actually the determinant of this, right? Fxx, fxy, fyx, fyy. Okay. So you kind of think about this is the x coordinate, this is the y coordinate. Okay. And this is the x coordinate, and this is the y coordinate, kind of. Okay. So you have a 2 by 2 matrix. You said f of x, fxx, fxy, fyx, fyy. Now the determinant of it is going to be exactly this value. Okay. This is going to be the determinant of it. Okay. That's where it comes from. So if it's easier for you to memorize as a determinant, that's fine. Some of you might say, hold on for a second. It's not, because you're going to get fxx times fyy times fxy times fyx. But we saw when we have continuous second derivatives, right? When we have continuous derivatives, these guys are going to be the same, right? fxy always equals fyx in that case. So you can assume it's actually fxy times fyx, but they're the same, so I just calculate one of them. Okay, so that's a lot of things going on at the same time. I think that's enough theory. Then we should do maybe some examples, huh? It's right about time.